Welcome to our next lesson. This is a review lesson for Calculus 1 on the topic of algebra. The previous lesson on arithmetic reviewed mathematical essentials. They're essential not because they're basic or easy, but because they provide the conceptual foundation for so much of calculus. These essential ideas are presented at a collegiate level to reflect the precise and formal nature of mathematics, to prepare you for this course and for mathematics courses you'll take after it. This lesson will review the following concepts: the concept of a set, the elements of a set and set notation, different types of intervals of real numbers, bounded and unbounded, how the real line helps define the Cartesian plane and Cartesian coordinates so we can talk about sets of ordered pairs, how formulas, identities, and equations differ, and some techniques for solving polynomial and exponential equations. The professor expects you to have some degree of proficiency in these concepts and techniques already. If you need more confidence, more practice, talk to the professor. Sets. A set is a collection of elements. In this course, we will be working with sets of numbers, and we will use various types of notation to represent sets. Simple set notation surrounds the list, using commas as separators, of elements in curly brackets, also called curly braces. Here's an example. The set of even numbers less than or equal to 10 can be written as curly bracket 2, 4, 6, 8, 10, close curly bracket. If our set is big, we can use an ellipsis, 3 periods right in a row, to shorten what you write as long as the pattern in the elements is clear to your reader. For example, the set of even numbers less than or equal to 100 can be written as this set with ellipses. Curly brace 2, 4, 6, 8, and having established the pattern of even numbers, we can write an ellipsis and then follow it by 96, 98, 100, the end of the set. Another convention in set notation replaces the list of elements with a precise description of the elements that take the form of the type of numbers in the set, for example, natural numbers or integers, and then defining conditions on those numbers, separating these two by a colon or a vertical line symbol. Here's an example. The set of counting numbers less than or equal to 100 can be written with an ellipsis in the first form, and that's the same as writing it as a type of number with a condition in the second form. Take a minute to look at this. Pause the video if you need to. The set of counting numbers less than or equal to 100 can be written as this. First with an ellipsis, second with the numbers and conditions. In the second of these expressions, this E symbol means, quote, is an element of. So N, E symbol, capital N, means, quote, N is an element of the set of natural numbers, or, quote, N is a natural number. Here's another example. The set of even numbers less than or equal to 100 can be written in two ways. First, N is an element of the natural numbers, colon, which we read sometimes as such that N is less than or equal to 100, and N equals 2m for some m in the natural numbers. Another definition would be curly bracket 2m, such that m is a natural number and 2m is less than or equal to 100. A type of set we will use very often is the interval of real numbers. Here's an example. The interval from 1 to 3 is the set of all real numbers that are bigger than or equal to 1 and smaller than or equal to 3. In set notation, it looks like this. A type of set we will use very often. Let A and B be real numbers. Then the set AB is the closed interval from A to B and is defined as follows. Read it closely. The set AB is the open interval from A to B and is defined as follows. Look at it closely. The numbers A and B are called endpoints of these intervals. Notice how a bracket or a parenthesis reflects whether or not the endpoint is in the interval or not. Open and closed intervals can be expressed on a real number line e.g. on an axis, in one of two ways. On the left, we have representations for the closed interval. You can see at the top it has the interval notation for the closed interval AB. And on the right, there's interval notations, or notations for the open interval from A to B. The first representation on the real line for the closed interval has the square brackets at the endpoints, reflecting the interval notation. On the right, the endpoints of the open interval are parentheses, also reflecting the interval notation we use. On the bottom, on the left, for the closed interval, the endpoints are represented by filled-in circles. And on the right, for the open intervals, the endpoints are represented as open circles. Notice how the open circles correspond to parentheses, where the endpoints are not included in the intervals, and the closed circles correspond to square brackets, where the endpoints are included in the intervals. Boundedness and unboundedness. A set of numbers b is bounded above if there's a number m that is greater than or equal to every element of b. That is, if x is less than or equal to m for all x in b. The number m is called an upper bound for b. A set of numbers b is bounded below if there's a number little m that is smaller than or equal to every element of b, i.e. if m is less than or equal to x for all x in b. The number little m is called a lower bound for b. If a and b are finite numbers, then the intervals with a and b as endpoints are bounded above and below. To see this, take capital M equal to b as an upper bound, and take little m equals a as a lower bound. If a set b is not bounded above, we say it is unbounded above. This means that for any number capital M, there is an element of x, or if a set b is not bounded above, we say it is unbounded above. This means that for any number m, there is an element x of b that is greater than m. That means there's an x in b where m is less than x. Similarly, if b is not bounded below, we say it is unbounded below. This means that for any number little m, there is an element of b that is less than or equal to little m. That is, there's an x in b where x is less than m. Unbounded intervals take one of the following 5 forms. Please pause the video if you want more time to study the 5. Notice that we use a parenthesis on the infinite end of an interval because plus or minus infinity is not a number and cannot be an endpoint. Sets in the Cartesian plane. Another type of essential set are the sets of points in the Cartesian plane, or sets of ordered pairs of real numbers. Think of the Cartesian plane as a perfectly flat tabletop that extends infinitely in all directions, with a pair of real lines, which we will call real axes, laid on top in the following way. They cross one another at their 0 locations, we call this point the origin of the coordinate system, and they intersect at a right angle. This pair of real lines arranged in this way define a coordinate system on the plane. A coordinate system is literally a frame of reference for the points in the plane. This diagram shows how the real axes are arranged with respect to one another. This diagram should be familiar. Pause if you want to study it for more time. The two axes, which we will call the horizontal axis or the x-axis, and the vertical axis, or the y-axis, give us an unambiguous way to identify the exact location of any point in the plane. Let's do that now. So let P be a point in the plane. The ordered pair identifying the location of P is found as follows. Draw a line from P to the x-axis so the line is parallel to the y-axis. This line will intersect the x-axis at a number we call A. Draw a line from P to the y-axis so the line is parallel to the x-axis. This line will intersect the y-axis at a number we'll call B. The two numbers give us an ordered pair, AB, that precisely describe the location of the point P. In the ordered pair, the first number is the horizontal distance of p from the origin, and the second number is the vertical distance of p from the origin. This example shows you a set of 5 ordered pairs and how they are located in the Cartesian plane. Take a moment to study this example to make sure you understand it. Solution sets to equations. A mathematical expression is an algebraic combination of constants and symbols. Examples of single variable expressions are shown here. We evaluate an expression by replacing the symbol x with a real number and simplifying the expression to a single number. Study this example where we start with an expression and we evaluate it at a value for x, the square root of 3. Notice, evaluating the expression gives us an exact answer, in this case, root 3 minus 2. If allowed, we can convert an answer to a decimal, which we often view as an approximation. In this case, root 3 minus 2 is approximately equal to negative 0.267949, and the decimal expansion goes on. Any finite decimal expansion of this number would be an approximation. Comparing quantities, formulas, identities, and equations. In this class, we have 5 symbols that we use for comparing real numbers. Less than, greater than, less than or equal to, greater than or equal to, and equal to. You should know what each of these symbols means and how to use them. You've already seen how we use the inequality symbols to define intervals of real numbers. Next, we focus on 3 ways we use the equality symbol. The equal sign is used in formulas. A formula is a mathematical expression that shows how one quantity can be expressed in terms of one or more other quantities. We show several examples of formulas. Let A be the age of one child, and let B be the age of a child that was born on the same date, but 4 years later than the other child. We can write a formula for A in terms of B as A equals B plus 4. Here's an example from business and economics. A wholesale box store sells goods for 20% less than their retail prices. If W is the wholesale price of a widget, and if R is the retail price of the widget, then we can write a formula for W in terms of R as W equals 0.8 times R. This next example is from chemistry. The ideal gas law is a formula that shows how the pressure, P, temperature, T, and volume, V, of a gas are related. The law says temperature is jointly proportional to pressure and volume. We express this as the formula T equals alpha times P times V, where alpha is a real constant. Another formula example, the area of a rectangle is A. The rectangle is L units long and W units wide. If A represents the area of the rectangle in square units, the formula for area in terms of length and width is A equals L times W. The next example concerns circles. If A represents the area of the circle in square units, and if C represents the circumference of the circle in units, we can write formulas for both area and circumference in terms of the circle's radius, measured in units, as follows. A equals pi times r squared, and C equals 2 times pi times r. Identities. An identity is an equality that is valid for all values of the unknown in the equality. For example, you should be familiar with these 2 Pythagorean identities from trigonometry. Sine squared plus cosine squared equals 1, and 1 plus tangent squared equals secant squared. You should also have experience proving identities, and you should have experience using identities to simplify expressions. Another important trigonometric identity is the sum and difference identity for sine. I will let you pause the video and you can review the identity. Some identities involving inverse trigonometric functions include these. Equations. An equation is an equality that is valid for some real values of an unknown or for no values. A solution to an equation is a value of the unknown that makes the equality true, i.e., evaluating the left and right-hand sides at a solution gives the same number. The set of solutions to an equation is called the equation's solution set. Here are 3 examples of equations that have no real solutions. Can you figure out why? Each equation is like a mystery challenging you to find its solutions. Determining which values of the unknown satisfy the equation is known as solving the equation. Here are 3 examples of equations that have 1 or more real solutions. The last of these has an infinite number of different solutions. Linear equations. Different types of equations require different techniques to solve. In your pre-calculus course, you learned how to solve many types of equations. Linear equations, those of the form mx plus b equals 0, can be solved with simple arithmetic. A linear equation with m not equal to 0 always has one solution. Solutions to quadratic equations, ax squared plus bx plus c equals 0, can be found using the quadratic formula. The quadratic formula says all solutions to quadratic equations, like that one above, have the following form. The quadratic formula says, the expression b squared minus 4ac is called the discriminant of the quadratic. Notice if the discriminant is negative, there are no solutions. If the discriminant is 0, there is one solution, and if the discriminant is positive, there are 2 distinct solutions to the quadratic equation. Knowing the solutions of a quadratic equation tell us about the factorization of the polynomial. If this quadratic equation has one solution, call it alpha, then we can rewrite it as a times the quantity x minus alpha squared. If the quadratic equation has 2 solutions, call them alpha and beta, then we can rewrite the quadratic expression as a times x minus alpha times x minus beta. If the quadratic equation has no solutions, we say it is irreducible. The previous slide illustrates an important relationship between the solutions to a polynomial equation and the factorization of the polynomials. The following theorem tells us how many solutions we can expect of a polynomial equation of degree n. A polynomial of degree n can be factored uniquely into a product of linear or irreducible quadratic factors. The degrees of the factors sum to n. This is the fundamental theorem of algebra, and it guides us in our searches for zeros of polynomial equations. So it's important to be clear about the relationship between a solution to a polynomial equation, p of x equals 0, and the factorization of p of x. If p of x is a degree n polynomial, and if alpha is a solution to p of x equals 0, sometimes we call alpha a 0 of p of x, then there is a degree n minus 1 polynomial, call it q of x, for which p of x is the quantity x minus alpha times q of x. If we know alpha, we can calculate q of x using polynomial division. The distinction between formulas and equations can be blurred, and that's okay. Take the Cartesian definition of a circle of radius 1 centered at the origin. Here's the formula. The equality in this definition is both an equation, the circle is the set of its solutions, and a formula, it defines a circle. To find ordered pairs of points in the unit circle, choose a value for x, evaluate the equation at that x value, and then find the values of y that solve the remaining equation in one variable. For example, if we take x equals 1/2, the defining formula for the circle becomes x squared plus y squared equals 1, then becomes 1/2 quantity squared plus y squared equals 1, and then continuing to solve, we end up with y equals plus or minus the square root of 3 over 2. So the points 1/2 comma root 3 over 2 and 1/2 comma negative root 3 over 2 are on the circle. In contrast, take x equals 2. The defining formula for the circle becomes 2 squared plus y squared equals 1, which simplifies to y squared equals negative 3. This equation has no solutions, so no points in the circle have an x-coordinate equal to 2. Another important type of set defined using set notation is the graph of a function. You have worked with functions in previous mathematics classes, so you have certainly seen this before, and we will review this in more detail in the next lessons. Suppose f of x is a function. The graph of f of x is a set of ordered pairs, x, y, such that y equals f of x. Some examples. An exponential equation has its unknown in the exponent. The simplest exponential equation looks like a to the x equals b. Equations with exponents. An exponential equation has its unknown in the exponent. The simplest exponential equation looks like a to the x equals b, where a and b are positive real numbers. The essential techniques for solving an exponential equation rely on logarithms. For example, we solve the above equation by taking the logarithm of both sides and using properties of the logarithm as follows. You can see we end up with x equals the natural log of a over the natural log of b. We conclude with a slide to remind you of another set of mathematical logs. Akin to the law of exponents that were reviewed in the previous lesson, there are laws of logarithms that give us identities for logarithm functions. For example, we solve the above equation by taking the logarithm of both sides and using properties of the logarithm. For a and b positive reals, and for x any real number, logarithms have the following properties. Please review these by perhaps pausing the video. This lesson has reviewed the following concepts: the concept of a set, the elements of a set and set notation, different types of intervals of real numbers, bounded and unbounded, how the real line helps define the Cartesian plane and Cartesian coordinates, so we can talk about sets of ordered pairs, how formulas, identities, and equations differ, and some techniques for solving polynomial and exponential equations. The professor expects you to have some degree of proficiency in these concepts and techniques already. If you need more confidence or need more practice, talk to the professor. See you at the next review.